When you wait for a bus, you'd say the wait was about 8 minutes, not exactly 8.000. Time doesn't jump from one whole number to the next. Between 8 and 9 minutes lie infinitely many possible values. With a discrete variable, like the number of heads in 3 coin tosses, we drew a bar chart. Each bar's height was the probability of one exact value, and the bars added up to 1. But waiting time isn't a handful of values. It's a whole continuum. So slice it finer. Use more, thinner bars, each covering a smaller sliver of time. Keep shrinking the bars, and their jagged tops smooth out into a single continuous curve. That curve is the probability density function, the PDF, written f of x. It's the star of this lesson. Here is the crucial mental shift. On this curve, the height at a point is not a probability. Probability is area. The shaded region between A and B is the chance the value lands between A and B. In the language of calculus, that area is an integral. You add up the curve's height across the whole interval. This distinction has a striking consequence. Because height is density, not probability, the curve is allowed to rise above 1. Watch. Take a flat density that sits at height to over the interval 0 to 1 half. Its total area is 2 times 1 half, exactly 1. So it's a perfectly valid density, even though the curve pokes well above the value 1. Only the area has to behave, never the height. Now a fact that surprises everyone the first time. For a continuous variable, the probability of hitting any single exact value is 0. Not tiny, exactly 0. Let's see why. Ask for the probability at the single point A. That's the area of a slice with no width at all, just a vertical line. And a line has 0 area. There's nothing to shade. Formally, the integral from A to A is 0 because the top and the bottom limit are the same point. One neat payoff of this. Since the endpoints carry 0 probability, it makes no difference whether you write less than or less than or equal. Strict or not, all 4 of these intervals have the very same probability. So which curves even count as densities? Just 2 rules. First, the curve can never dip below the axis. A density is never negative, because no region can hold a negative probability. Second, the total area under the whole curve must equal exactly 1, because the value is certain to land somewhere. All the probability added up is 1. Those are the only 2 conditions. Any curve that stays non-negative and encloses a total area of 1 is a legitimate probability density. There's a companion to the density worth meeting. The cumulative distribution function, or CDF, written capital F of x. It answers one question. What's the probability the value is less than or equal to x? Picture sweeping a vertical line from left to right. As it moves, it sweeps out area under the density. And that accumulated area, so far, is exactly f of x. It's the running total of probability. See its shape. It starts flat at 0 on the far left, climbs fastest where the density is tallest, and levels off at 1 on the right, because by then, all the area is behind you. This gentle S is the signature of a CDF. These two views are two sides of one coin. The CDF is the accumulated area under the density. And running it backwards, the density is the slope of the CDF, its rate of climb. One more handy consequence. To get the probability of an interval, just subtract two CDF values, f of b minus f of a. Let's earn all this on a concrete density. Suppose f of x equals some constant c times x on the interval 0 to 2 and 0 elsewhere. Two jobs: find the c that makes it a genuine density, then compute the probability that x is at most 1. Rule 2 is our lever. The total area has to be 1. So integrate cx from 0 to 2 and set it equal to 1. The antiderivative of cx is c times x squared over 2. Evaluate from 0 to 2, c times 4 over 2, which is to c. to C equals 1. So C is 1 half. Our density is f of x equals 0.5x. Now the probability. With C pinned down, f of x is 1 half x, a straight line climbing from the origin up to the point 2, 1. The probability x is at most 1 is the area from 0 to 1, a triangle. Its base is 1 and its height. The value of f at x equals 1 is 0.5. Integrate 1 half x from 0 to 1 and you get 0.25. And the triangle agrees 1 half times base 1 times height 0.5 is also 0.25. Area and integral, the same answer. The simplest continuous distribution of all is the uniform. Here, every point in an interval a to b is equally likely. No favorites. So the density is perfectly flat. A horizontal line of some height k. What must the height be? The area is just a rectangle with b minus a times height k, and it has to equal 1. So k times b minus a is 1, which means k is 1 over b minus a. So here's the whole uniform distribution on a page. The density is 1 over b minus a between a and b, and 0 outside. And stating that outside part matters, it's part of the answer. And its CDF rises as a straight ramp. Flat at 0 before a, climbing linearly as x minus a over b minus a across the interval, then pinned at 1 past b. Two more formulas worth memorizing. The mean sits dead center at a plus b over 2, and the variance is b minus a squared over 12. Let's use it. Your cab's weight, in minutes, is uniform between 5 and 15. We'll find three things. The chance the weight is between 7 and 10, the chance it's over 12, and the mean and variance. First, the density. b minus a is 10. So f of x is 1/10 across the whole span from 5 to 15. For the chance the weight is between 7 and 10, shade that strip. Its width is 3, its height 1/10. So the area, the probability, is 3/10, 0.3. Next, the chance the weight exceeds 12. That's the strip from 12 to 15, again with 3, height 1/10, so again 0.3. You can also do it with the CDF as a check. F of 12 is 12 minus 5 over 10 7/10, and the probability of being above 12 is 1 minus that, which is 0.3. Both routes agree. Finally, mean and variance. Straight from the formulas. The mean is 5 plus 15 over 210 minutes. Right at the midpoint, exactly as a flat distribution should be. The variance is 15 minus 5 squared over 12. That's 100 over 12, about 8.33. Your turn now. Here's a fresh one. X is uniform between 2 and 6. Pause the video and find the probability it's between 3 and 5, plus the mean and the variance. I'll wait. Here's the walkthrough. b minus a is 4. So the density is 1/4, 0.25. The strip from 3 to 5 has width 2, so its area is 0.25 times 2, 1 half. The mean is 2 plus 6 over 2, 4, the midpoint. And the variance is 4 squared over 12, 16 over 12, about 1.33. If you landed those, you've got this cold. Trap 1. Expecting the probability at an exact value to be some small positive number. For a continuous variable, it's exactly 0. Only intervals of real width carry probability. Trap 2. Reading the height f of x as a probability. It's a density. To get a probability, you must integrate it over an interval. Measure an area, not a height. Trap 3. Insisting the curve stay below 1. It needn't. The density can rise as high as it likes. The single unbreakable rule is that its total area equals 1. Trap 4. For a uniform, writing 1 over b minus a and stopping. Incomplete. You must say where it applies, between a and b, and that it's 0 everywhere else. Let's lock it in. For a continuous variable, Probability is area under the density, the integral of f from a to b. A curve qualifies as a density when it's never negative and its total area is exactly 1. The CDF capital F of x is the probability of being at or below x. The density's accumulated area rising smoothly from 0 to 1. And the uniform distribution is your model case. A flat density 1 over b minus a mean at the midpoint, and variance b minus a squared over 12. Hold on to these, and continuous random variables will feel like second nature.